So let's start. So we are doing this Feynman's theorem, as we recall. Started this proof. So this is continued. So I won't write what we left off. So I start from where we left off last lecture. So just to get an idea, let me look at a special case. For this example, if you understand this example, you understand everything. That's it. So a special case. Well, this special case is where S of x is equal to 1/2 the xx. This is quadratic part, and there is minus g2 or g3 rather, b3 over b factorial minus g4 b4 over 4 factorial. So of those infinite g's, we just select two, g3 and g4. Of course, b3 and b4 are just tensors, rank 3 and rank 4, symmetric tensors rank 4. But we can consider them also as functions when you compute on the diagonal. This is a cubic function, it's a quartic function in d variables, for example. And what we want to compute is the following integral as a formal power series, as we discussed. So h bar to the power minus d over 2 integral of d exponential of minus 1 over h bar s of x dx. And I explained last lecture that this makes sense as a formal power series. It may be divergent or convergent, it doesn't matter for us. We just look at it as a formal power series, and we know how to make sense of it as a formal power series. With this one, so then the change variable x equal to root h bar y. Then this gives us this partition function now, z becomes equal to this thing cancels, and we get rid of this h bar in front of, this is devised in order to get rid of h bar from the front of bxx, basically. Because that's what, again, we have a standard formula for that for the Gaussian. So this becomes equal to integral over RD again, exponential of minus d y over 2, a Gaussian, times exponential of some stuff here. I don't write this stuff, but you know what that stuff is. So then the point is that this becomes equal to z. Now, as a formal power series, if you do the move, becomes equal to basically, so integral, so I would say sigma m and n belonging to z, actually in this case, m and n bigger than or equal to 0, integral over RD, exponential of minus 1/2 b y, and then times tau 3 to the power m, b3 to the power m, divided by m divided by 3 factorial to the power m over m factorial times tau 4 to the power n, b4 to the power n, 4 factorial to the power n times n factorial. Now, what are these funny coefficients now? So these are just tau 3 is equal to g3, just for the matter of writing, g3 h bar to the power 3 over 2 minus 1. And tau 4, similarly, it's just G4 H bar to the power 4 over 2 minus 4. So these are rescalings of G3 and G4 that with respect to H that happens when you do change of variable here in these tensors. They get these powers of H in front. So just, and how to get this, obviously, we just, what we did here, we just, this exponential of G3 and G4 terms, we just write exponential of A plus B. We just use this simple formula. They commute when these two things are commuting, so this is equal to sum A to the n over n factorial, E to the n over n factorial, and then bigger. That's what we get from the explanation. So, and binomial coefficients. So now the point is that we just now we're going to use Wick's theorem to compute each summand here, because this guy now is exactly ready to apply Wick's theorem to, because this is just a monomial to some power, again is a monomial, and then the whole thing is a monomial in y1 up to yd, some sums of monomials basically, right? So we use Wick's theorem to compute this. Okay, so now to do that, sorry, we get the following kind of diagram of pairing. Sorry. So we create some flowers like this. These are like 3 valent flowers, and then here. So we put m of them, which was from this previous page, m trivalent flowers. And here we put n trivalent flowers, 4 valent, sorry. Get that before. And we do n here, right? Okay, so now let the T equal to set of pairings of these half edges. Set of pairings so actually I want for this T to be the set of half edges themselves, not pairings. It's called set of half edges. Now Wick's theorem. Okay, so Wick's theorem tells us that to compute such a thing, we have to create all kinds of pairings of these half edges, and then contract, and then you get the final weight of the thing, and then you have. So let's consider, for example, one example would be something like this. You connect these two half edge. You connect this half edge over here. You are allowed to do that. Let's connect this to that, and then this to this, and this to this, and you do completely on both sides. So when you do this, so for sigma, so a pairing of half edges, when you do this move, you get a graph. You get a bona fide graph, not pairings anymore. So get a graph which is denoted by gamma of sigma. So this is a very crucial step that we go from pairings to graphs. Okay, so this is a move that has amazing consequences. Pairings to graphs. Okay, then so then Feynman, then Big's theorem actually, not Feynman's. So then Big's theorem. So let me tell you what happens in this case. So imagine you have m equal to 2, and n is equal to 1. Then you get the graph, the following graph, like exactly what I drew there. You get the graph with 2 trivalent vertex and 1 for a 4-valent vertex. This is this one trivalent vertex here. So you get the graph, which is, and then we've got we have this, which is nothing but the kind of, I don't know what's it called. This is a kind of dumbbell graph or something like that. Get this. So here, that's the technology that takes us from pairings, which is huge number, to graphs, which are much less. And you will see what is the point of this move. So in any case, so Big's theorem tells us that this quantity star, that the z actually is not z. So let me write it here again. Integral over RB exponential of -1/2 b y. I don't know this tau 3 to the power m over 3 factorial to the power m n factorial times tau 4 to the power n over 4 factorial to the power n factorial is equal to, so it's exactly the same coefficient. This is just times, I should put times the exponential of, there should be b3 to the power m, sorry. That's the crucial part. And then b4 to the power n, right? This quantity that we want to compute is equal to.
Right, Masoud, there's a question.
Yeah.
You drew 2 graphs there. What's the second graph? Where's that come from?
Oh, this one?
Yeah.
This one is exactly this.
Okay.
So I just put it like this. Oh, I have to put this here as well.
Okay.
Sorry.
No.
That was the point. Yeah. Right. I missed to put this edge there. So there's a theta graph and there's a circle connected. So it's not dumbbell graph. Yeah, I made a mistake. Thanks for pointing this out. That was great. Okay, so this now is equal to, now let me write it here. So this is equal to this quantity is actually equal to yeah. So this is good. Let's call this quantity star now. So Big's theorem said that star is equal to 2 pi. Okay, so this is like determinant of this is the Gaussian part, 2 pi over b, tau 3 now, the power m tau 4, the power m over 3 factorial, power m factorial, 4 factorial, power n factorial, sum. It's a constant, this is also a constant, but this is sum sigma f sigma. Sigma belongs to pairings of T, right? That's what Big's theorem tells us. So this f sigma is the Feynman weight of Feynman amplitude, whatever, of pairing sigma. Right. That's that. Now, now we just observed that actually it's easy to see that F sigma is equal to F gamma of sigma. So in other words, the Feynman rules for graphs is actually compatible with Feynman rules for these one-valent graphs that we have there. So now to see this, I'll give a proof later on, but it's not difficult. I mean, if you think about this, you just put it in front of yourself and look at it for maybe a few minutes. You can. Okay. So this is for any sigma belonging to pairings of this set of averages. Okay. But the point is that, and this is the difficulty, different sigmas correspond to the same graph, could correspond to the same graphs, okay? Different sigmas can come from same graph, same pairing, I'm sorry. Different graphs, I should say. Different, okay, so no, different pairings can give rise same graphs. It's better to say it. Can give the same graph. Okay, so in other words, the map from pairings of sigma, I mean pairings of t to these graphs is not injective. I mean the map is non-injective. Remember, we are summing over here first. We are supposed to sum over these guys, right? But we want to we are trying to write the sum as sum over these ones to simplify. Question?
What exactly is F sigma?
Oh, F sigma?
Yeah.
Oh, F sigma is what I did maybe in the second lecture when I discussed the Biggs theorem. So F sigma is like this. So imagine you have like 4 vertex. So the pairing is a one-valent label graph. So if it's like this, so you have here 1, 2, 3, 4. You have the inverse 1, 2. This is the inverse 3, 4, and you multiply this together.
Thank you.
Yeah, sure. Okay. Cool. Okay, now and B of course is this B. Yeah. Okay, so now but the one thing is obvious that all graphs are obtained this way. You see, but but all graphs are obtained from pairing. I mean, the proof of this is very easy to see because imagine you have like something like a theta graph. And if you want to see the pairing, you just cut it. You have one thing here, set of then flower here. And then you have another flower here. And then you connect according to. So you can do this for any graph that you want. As long as the type is compatible with your choice of M and N. So that's the thing. Now, so the difficulty is to understand now the kernel of this map in some sense. So how many points are in the fiber of this map, basically? How many points correspond to the same graph? How many pairings correspond to the same graph? So you see, how many pairings correspond to the same graph. That's the thing now. So now for this, let us define a group. Let G be the group of permutations of half edges of the set of half edges T that preserve the flower structure. That preserve the flower structure. What do I mean by this? Well, remember, let's recall, I mean, what the picture that we had, like we had one flower here, like three half edges here, and another. Okay, so another one, and so on. So we had like M of those, and then 4 half edges at each for each flower here. So flowers with 4 half edges each. So what we are looking at is the group of, okay, permutations of these things, but not all permutations. That's crazily big, of course. That is going to be n factorial over n is number of all half edges. We don't want that. We want only permutations that preserve the structure of flowers. Namely, it sends each, for example, flower to a flower again. So it doesn't send this, for example, to this, because this is going to be like a trivalent flower. This is a 4-valent flower. We don't want that. We want the structure to be completely preserved. Okay. So the order of this group then. What is the order of, so what are the elements here? Okay. So here we have got like M of those. And here we have got N of these, right? Okay. So certainly we can just do like I mean S3, 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 S3. All of it you can permute within each flower first. So it's going to be like S3 plus S3 plus S3. And we can also permute these 4 edges on each flower on the right hand side. Then this is multiplied by S4 plus S4 plus S4. Let's see how many we have got so far. So we have got 3 factorial to the, so we've got like, yeah, we have got like, yeah, 3 factorial to the power n. Here so far. 4 factorial to the power n. And now we can collectively permute these endings of flowers here within each group. So there are going to be Sn, which is n factorial here, and Sn, which is gives us n factorial. So times then 3 factorial. Okay, sometimes n factorial times 3 factorial. Okay, so this is the this is what we have so far. Okay. So 3 factorial to the power n times 4 factorial to the power n times n factorial times n factorial. We have seen this number. This is exactly the denominator of the terms that came from before weeks. And so this is an important thing. So now we just say that, okay, so order of G is exactly equal to denominator. I erased the star, but no, it's here. Basically, is equal to the denominator. Of the star. Okay. So then what's left to do now is to observe that G actually acts on the set of all pairings of T, and it actually acts transitively on each fiber. So that's the next thing you have to observe. Okay. So G acts transitively. I will explain what this means. That's okay. Transitively on the fibers of the map from pairings of these path edges to graphs. And what do we mean by this? I mean, if you have two pairings, or any two pairings, sigma 1 and sigma 2, belonging to pi of t, set of pairings of t, such that they correspond to the same graph, such that gamma of sigma 1 is actually equal to gamma of sigma 2, you are sure that there exists G belonging to G. There exists a permutation of the set of all pairings, this group G, such that there exists G belonging to big group G, which know its order, such that actually carries this pairing into the other one. So the situation is a bit like this. So we have this big set of pairings of T. We have the fibers of this map. So this is the set pi of sigma, pi of T. And this is the map that takes us into these graphs. Each fiber corresponds to a certain graph here. This fiber corresponds to another graph, this one. Now, this G acts on this pi of T, but the claim is that it's actually, well, it's not transitive, but it's transitive if you restrict it to a fiber. Since fiber to fiber is transitive. Again, this, you have to sit down and think about it. This is not difficult to see, but a little bit takes time to explain, and I'm not sure if I explain, it's going to be even more transparent after. So this is just, yeah, let's accept it. Okay, so then now how we count. So then let's count the number of stabilizers of a given pairing sigma, for that matter. And the group of stabilizers of a pairing sigma given pairing sigma is exactly is exactly the group of automorphism of the graph that corresponds to that. So this is exactly the automorphism of gamma. So imagine in the picture that we had at the beginning. So let's draw that graph again, like this. It was, remember, Okay. So this is the graph that we got by identifying pairings in the way that we defined. So this was gamma. So the question is, what is the automorphisms of these things? Well, the automorphisms here, to get the automorphism, you cut them in half. You just cut them, and you have to do permutations that preserves this structure again. So basically, the group of automorphism comes from the group of switchings in the pairing, but they have to be compatible with the with the structure that. Yeah. Okay, so this is that, but then I use very simple results from group theory, which is more or less you know what it is. So let me write it down. So then use the result. I mean, it can be formulated in terms of group actions, but I'm not sure actually. Yeah, I need that even. So basically, the result is this. Imagine if you have a map, homomorphism, a group map from one group to another group, H, surjective, then it follows that. At least this is a special case of what I need. I mean, what I need maybe is a little more general, but let me give it in this case. Yeah, so this it follows that the order of H, these are finite groups. Order of H is equal to order of G divided by order of kernel of, so this is called maybe alpha, kernel of alpha. If this is a surjective mapping, I mean, yeah, because H basically is isomorphic to this quotient space, and the order of the quotient space is exactly the order of G divided by the equation. Or kernel. Okay. So then basically, if we accept all this, then it turns out that yeah, it turns out that number of pairings sigma that gives the same graph gamma order is equal to order of this group divided by the order of other group, n factorial, n factorial, p factorial to the power m, and 4 factorial to the power n, divided by order of automorphism of yeah. So now we can use in the formula that we derived, we can write summation of all the final weights of these pairings that we needed, sigma belonging to pairings of half edges, is equal to summation over gamma belonging to graphs of type 3, 4. I put here M and N, and then I explain what this means, because I didn't want to write a much more general expression as we had before. This is 3 factorial the power m, n factorial, 4 factorial the power n factorial over automorphisms of gamma times f gamma. And if you put it into the formula, this numerator cancels that denominator, and only 1 over automorphism remains. So from here, then we get that. Okay, first of all, what is this? What is G and then 3, 4? This is, let me write it here, set of isomorphism classes. Isomorphism classes of graphs with M trivalent vertex and N four-valent vertex. So N goes with 3, N goes with 4, and N four-valent vertex. There's this one, and there is one more item left, and that's now we have to take care of that powers of H. We have to count the powers of H as well. Okay. What happens to powers of H? Because there was one power of H to the power 3 over 2 minus 1, and then we are raising the expression to powers M. And then another power H 4 over 2 minus 1. Yep. So let's see what happens to those. That's very important, actually, counting H powers. We have this tau 3 to the power n, tau 4 to the power n is equal to G3 to the power n. According to definitions, this comes out to be G3 to the power H bar to the power 3 over 2 minus 1 times n. Then there's G4 to the power n. And then 4 times H bar to the power 4 over 2 minus 1 times n, which we can write it as G3 to the power n, as we want, G4 to the power n, and then H bar to the power 3m plus 4n over 2 minus m plus n. And this is a familiar term. 3m plus 4n is exactly the number of edges, because for each vertex you have m, either m edges coming to that vertex or n edges, but you're counting this way twice, because you know, if you count based on vertices, you're counting twice each edge. So this number of edges with this factor here is equal to number of edges, but this is exactly number of vertices, right? Minus number of vertices. Okay. Number of edges. And this is the negative of Euler characteristic. This is equal to negative Euler characteristic. Yeah. So then this is proved. We prove for still of x, I mean, equal to G3 times D3 over 3 factorial plus G4, something like that, over 4 factorial times D4 over 4 factorial. But in general, if you have more terms, it's exactly similar argument. There's no difference. You just add more variables. That's it. Similar moves So that's the idea. I mean, one has to sit down and quietly do a little bit of checking some of these statements I made, but they are not difficult. Just yeah. For example, one statement I made was why f sigma equal to f gamma sigma. So I leave this as an exercise. So basically, exercise. This is actually a good exercise. Why f sigma is equal to f gamma sigma. You go through the definition of this contraction of tensors, and you spell it out, and you see that it fits. Okay, are there any questions or?
This,
Yeah.
we are taking the sum over all possible values of m and n.
Yeah, for this
the
example, yeah.
Yeah. So, but if m and n are such values such that not all, if we do not have all pairings, if there are still remaining half edges, then what do we do? So, for instance, if m and n are both equal to 1,
Yeah.
then there are some half edges left over.
No, there shouldn't be anything left over. I think it's gonna be fitting completely. Should be okay.
Because we have one trivalent vertex and when we have a quadrivalent vertex.
Oh, yeah, that's right. In that case, you get, for example, the theorem was that if you have an odd number of variables multiplied, in this case, 3m, and then it's going to be 0. So we declare those as 0. Yeah, that's a good idea. That's a good question. Right, we declare those as zeros. You know, in Wick's theorem, I just wrote the case when there are only even number of terms. The odd terms are 0 by symmetry argument. Yeah. Cool. Okay, so I think now the real thing is now to do one kind of good example, a simple good example, and then you'll see what this entails. Okay. All right. So here's an example. This is example 1. So we are in dimension 1. So let's consider this quartic partition function. Z is equal to 1 over pi integral minus infinity plus infinity exponential of minus 1/2 x2 plus g x4 over 4 factorial dx. So obviously in this case, h bar is equal to 1. We put h bar equal to 1. Constant. Okay, I mean, when you look at it, it's clear that we can just write z as, sum a n g n, n from 0 up to infinity, which actually starts with 1 plus a1g plus a2g2, so on and so forth. And so the question is, what are these AIs, these coefficients, right? We want to compute the coefficients of AI. So this is a lucky situation because we can compute the AI just by hand, and then we compare it with the result that you get if you apply Feynman's theorem, and we'll see that if they match or not. So that's the example we want to do now. Okay, so easy to find AI is directly in this case, right? We can find it directly because this is what is this? This you can just write. You can just expand this, and then we get. I don't write it, but because we know that this is equal to in fact an is equal to 1/2 pi integral minus infinity plus infinity exponential of -1/2 x squared x to the power 4n divided by 4 factorial to the power n times n factorial dx. By the way, again, let me emphasize when I say z equal to this, are according not to it's not the value. This is just a perturbative series that we assign. It's just a formal power series that we are able to assign to such things, right? And this series is actually divergent for all g's, no matter how small g is. Okay, but this is just expanding exponential, and you get this term. But this term is very easy. We already know by classic Wick's theorem. Of course, we know that an actually is equal to 4n minus 1 double factorial, right? Divided by 4 factorial to the power n times n factorial. This is what we get from Wick's theorem in this special case. You don't even have to use Wick's theorem. You can just prove these things by induction. Okay, so then I just write the values that we obtain here because I'm going to check them later on. So you get A1 equal to 1/8. You get A2 equal to 35/384. 84, yes. And then you get A3 equal to 385 over 307. These are easy to compute from this general formula, of course. So now the game is we compute these values using Feynman's theorem, right? So compute N1 using Feynman's theorem. So to compute A1, we have to count, first of all, we have to list our 4-valent graphs with one vertex. We have to get all 4-valent graphs. With one vertex. And there's only one of them. So this is this. Gamma is equal to this graph 8. Okay. So the what is the automorphism group of this graph? Now is a good example to try to compute the automorphism groups. So what is the automorphism of this graph? So you can do this, and then flip. So it's really Z2 plus Z2 plus Z2 So the order, the symmetry factor, order of out gamma is equal to 8. So this is I don't know, it's called symmetry factor. Yeah. Yeah. Okay, so F gamma, which is the Feynman weight of this graph, or Feynman amplitude, whatever, is just equal to 1 because there is we have to decorate. They put 1 here because this coefficient here. I mean, we put G here if you want. I don't know. We don't put. We just put 1 because you see the interacting term was G x4 over 4 factorial. So you can imagine there is a B4 here tensor, but this B4 tensor is really 1 constant because G we cannot negotiate. G has to be there. It's G4 actually, but we call it G, right? But B4 is 1. So when you do this, and of course here B, yeah. So here is what is B inverse. I mean, for this vertex, it's also 1 because our integral was like this, right? The B term here is the quadratic function is just has coefficient 1. So its inverse is also 1. So this is 1, this is 1, gamma is 1. Okay, so that's what and then of course, Feynman theorem tells us that A1 is equal to F sigma, F gamma, sorry, divided by order of gamma, and it's equal to 1 over 8. And this is what the other calculation also tells us to be the case. Right? Question? Okay. All right, so now let's compute A2. That's kind of a little more fun to compute A2 next. I'm not going to erase these. Okay, so the standard, the direct method without Feynman gives us A2 equal to 35 over 384, right? And now we want to compute A2 using, so A2, we have to actually list all 4-valent graphs with 2 vertices, right? List all 4-valent graphs with 2 vertices. Right? Okay, first of all, there are those which are connected and disconnected. Let me list the disconnected ones first. So there is this gamma 1, for example, which is this one. There are 2 4-valent like that. There's gamma 2, which is this. Oh, this is connected. This is connected, sorry. Yeah, that's okay. And then there is gamma 3. There are actually 3 of them, yeah, in this case. This. Yeah. So there is 1 disconnected and 2 connected. So we get total 3 graphs. Yeah. So then we have to, okay, so we have the list of graphs that we want. Then we have to compute automorphism group of each. Let's compute that. For example, for gamma 1, what is the order of automorphism group of gamma 1? this is basically, I mean, the group itself, let me just write it. I just wrote it like this, is equal to Z2 to the power 3 cross Z2 to the power 3 cross Z3. Or gamma 1. I mean, this Z2, you can see that it comes from this switching these two factors. And Z2 to the power 3 is for each of those that we have this factor of 8 here, and then so the order of automorphism groups of gamma is equal to 8 to the power 2 times 2, which is 128.
May I ask a question?
Oh yeah,
Is it combinatorially known, like how many graphs with how many k-valent graphs with n vertices we have? Is it known?
no, I don't think so.
Ah, I see. Got it.
Yeah. This is oh, I'm not an expert on graph theory or anything like that, but I believe this is actually this is a not even polynomially solvable problem, so that's quite tough.
Ooh, that's bad.
Yeah, even for trees, we'll come to trees soon. Counting label trees is easy. That was done by Khalkhali, and we'll do it also with a different method. But knowing all trees with n vertices, there's no formula for that.
Interesting.
Yeah, because trees really are much simpler in a way. I mean, yeah. I mean, yeah, but I encourage you to actually check this for yourself. I mean, don't rely on what I'm saying. I believe there's no formula in general. Because it could be that the case of trees is that you're like looking at a subset of a set. I mean, the original set, there may be formula for the number of elements of that set, but not for that particular subset. So that's so what I'm saying does not imply what I was claiming. So check it yourself. But I believe there's no formula. I don't know.
Got it. Thanks.
Yeah, but if you checked it and find any result, let me know. Okay, that's a good question.
Sure.
Okay, excellent. So then we look at automorphisms of gamma 2 or gamma 2. This is S4 cross S2. I mean, this is S4. You're switching all these bands. I mean, you're permuting the bands. And there is also S2, which is changing the two vertices, swapping the two vertices. Okay, so this is S4 plus S2. So then the order of this guy is 48. And automorphisms of gamma 3 this is 2 to the power 4. I mean, yeah. Okay, so let me write it. So its order then is 16. Now, why is that 2 to the power 4? Well, you can see there is a Z2 here. There is a 2 here, there's a 2 here. But then there is also swapping this with that. But we cannot swap this with this because this will destroy the connection to this one. So computing automorphism can be tricky. I mean, there's some algorithm that you can compute, but I mean, I won't discuss that. But there's a very precise algorithm that gives you. It's a kind of linear algebra algorithm, actually. If you write the matrix of the graph, then the algorithm tells you how to solve the problem linear algebraically. Yeah. But yeah. Okay, so now the thing. So what is A2 then? According to Feynman's theorem, we write this. So it follows that A2 is equal to, actually Feynman's theorem tells us A2 is equal to 1 over order of out gamma 1 plus 1 over order of out gamma 2 plus 1 over order of out gamma 3, right? Because f gamma is 1, so the numerators are all 1. It doesn't matter. It's just 1. Because we are multiplying 1, 1, 1, 1 all the time. Okay, so in this case. Okay, so then we get, so this is equal to 1 over 128. I believe so, yeah, 128. Plus 1 over 48. Plus 1 over 16. And that's exactly, you calculate that, you get 35 over 384, which is what we have here from the other one. I mean, this kind of, when you write it down, it gives you all kinds of interesting relations between these fractions and the fraction that you get by computing factorials. So that's a verification. I mean, you know the theorem is true, but it's good to verify in some case. Okay. So now let me give you another example. So this example is actually related to a very important concept called free energy, which is we don't have to know what free energy means. It's a really pillar of statistical mechanics and quantum field theory, but it doesn't matter much. What it is really is log of partition function. So we denoted by f equal to log of z. This is a quantity of interest, even more than partition function. Log of partition functions of interest. And so one question is, what do we mean by log of this expression? This is the formal power series, right? Sorry. So recall logarithm of a formal power series. The only thing, the condition that it has to be the constant term, not 0. That's the only thing. Like, e.g., I just write 1 plus a1g plus a2 g2, so on, is defined using the formula. So we use the formula from calculus. I hope you remember log of 1 plus x. You remember log of 1 plus x. You remember? Autumn?
So 1 plus.
There's no 1. It should starts with x. Because if you put x equal to 0, log of 1 is 0. So it starts with non-constant.
So x plus x square over 2 plus.
Is it plus or minus?
I think it should be minus
It should be minus.
because it's
X minus 1/2 x squared plus 1/3 of x cubed minus 1/4 of x4 and so on. And if you are in doubt, what you can do, you can check that the derivatives of both sides coincide and the constant terms also match, then they're going to be. So let's take the derivative of this guy is going to be 1 over 1 plus x, and the derivative of this guy is going to be 1 minus x plus, which is 1 over 1 plus x, geometric series. But there is a issue of constant term. But constant term is also fine, because if you put x equal to 0, here you get 0, and here also you get 0. Right? So this is calculus. Right? And that's exactly what we use. Okay. So then, in this case, we just say, so log of So we just say, I mean, this is not a conclusion, it's a definition, log of 1 plus A1G plus A2G2, so on. We just see this as X now, as X. And then we just write it as X minus 1/2 X squared plus 1/3 X cubed, right? So on. Now, the only thing that you have to make sure is that this makes sense. In other words, you are not adding infinite number of terms for a fixed power. But that's clear because as you move on, the powers of G is increasing. You see, here it starts with power 1, here it starts with power 2, and so there is no power fund creeping in from higher terms to the first order. So this is well defined. So this is a well-defined power series. In other words, in G. Okay, so this is important. Okay, now, so this is the log of the partition function. So f equal to log of z is defined as a power series in G1, in G0, G1, G2. I mean, I did one variable case, but you can do it in many variable cases. Okay. So we have that. But then we will prove or see a beautiful theorem that tells us that, so it's a fact. We'll see this soon. That actually, in order to compute the log of the partition function, you have to sum, you only sum over connected graphs. That's the very important reduction. Again, another reduction. So from pairings, we went to graphs. Now from graphs, we go to connected graphs, which reduces the number of possibilities. It's equal to sum over connected graphs. So if you want, basically in this case, then you're claiming that this guy actually is equal to so let me write it now. I don't need this. Okay, so this is, you just write it as sum Fn Gn. Now n is bigger than or equal to 1, there is no constant there. Right? And Fn is equal to, okay, so let me write it here. Fn is equal to sum gamma belonging to connected four-valent graphs, connected. So let me put it this way: connected four-valent graphs with n vertices. Okay. Yeah. And 1 over. I mean, they are looking at a special case in this case, 1 over order automorphism groups of those gammas, which are connected. Okay. Okay, so now let us test this claim in this case, this theorem in our example. Okay. So first of all, I mean, what happens to our example? So we just had that f equal to log z turns out to be equal to log of 1 plus a1b plus a2 g2 1. If you use these values towards this formula, then you get an expression which starts with 1 over 8 G, this is obviously A1 plus 1 over 12 G2. And then some coefficient G3 and so on, which are more complicated to compute, but it's just calculus to compute those higher order terms, that's okay. Because some coefficient G3 plus some coefficient G4. So all I want to do now is to check that this A2 is, I mean, A1 is easy, but I want to check that A2 is okay. This is A2. I mean, it's not A2. I mean, this is another, should be given a different name. This coefficient is okay. Well, this is F2 actually, right? This is F2 according to this. So now let's check that because we have all the tools. So for n equal to 2, we have just two. We saw that actually only two connected graphs, 4 valent, 2 vertices. Just two connected graphs. I mean, 4 valent. 3 vertices. So then this tells me that, so these are the graphs that again, I just write it here. So this was one of them. And the other one is this one. That we had before, right? So the order of automorphism group of this one is 48. So this symmetry factor is 1 over 48. And this one is 1 over 16. So if you add these two things, you get 1 over 12. And this is exactly 1 over 2. As it should be, but it also fits the calculation that we want. So it fits the other information. So when I was doing this, I was so encouraged that I tried to do A3 as well. So I listed all 4 valent graphs with 3 vertices. I mean, why not? Let's maybe just check it to get something very interesting. Any questions? Okay, so let me at least list this thing because that's kind of interesting. So all, so for A3 in other words, to compute A3, we need all 4 valent vertices, I mean 4 valent graphs, sorry, with 3 vertices. Okay, so let's put the disconnected ones first. Okay, so these are 3 H graphs. That's one. Then there is this disconnected graph. There's this one. And there's another one which is then there is 8. Okay. So there is gamma 1, gamma 2, 3. So these are disconnected graphs. So then if you compute the order of automorphism group of here, this order of automorphism, in this case, you easily compute that's actually, okay, so let me write the answer and then I'll tell you why. You get 3072. Yeah. 3072. This is actually equal to 3 factorial times 2 to the 2 times 2 factorial to the power of 3. If you think about it, you get that thing. For this one, the order of automorphism group is actually equal to 16 times 8, which comes out 128. Okay, and for this one, the order of gamma is actually equal to 48 times 8, which is 384. You can easily change that video. Correct. Then let's look at connected ones. Let me connected paths. So there are like this one, double-edged triangle. So this is the double-edged triangle. There is a looped triangle. Looped triangle. And there is some sort of theta and loop. This one. And simply the last one is just simple. There are 4 of them. 1, 2, 3, 4. Yeah, that's 4. And this is going to be this one. And this is another one. And then there is a loop. Okay. So these are all the connected 4-way length graphs with 2 vertices. These are all the disconnected ones. And the order of automorphism groups here, this is order of gamma. Here is again 48. For this one, you get order symmetry factor again is 48. For this one, you get 24. And then you get 32. So then, lo and behold, if we add all these 7 numbers, inverse of 7 fractions, we have to get that quantity A3 that I calculated, I showed before, right? Which is 385 divided by, so let me write it down, which I did actually calculate. So here, I just write here, sum 1 over order of gamma, sum over connected ones, connected sum. This is 1 over 3072 plus 1 over 384 plus 1 over 128 plus 1 over 48 plus 1 over 48 again plus 1 over 24.
This will not just be the connected sum, right?
Sorry,
This is not just the connected sum, right?
connected ones? Oh, not connected. Sorry. Yeah, exactly. So this is basically all 4-valent 3-vertex graphs. All 4-valent. Thank you. 3-vertex. Yeah, exactly. And if you do that, this is equal to 385 over 3072, which is indeed a tree. And this actually, so what we know from the first calculation, that this is equal to the value of, I mean, this is 4n minus 1. Again, double factorial over 4 factorial to the power n. Right, times n factorial. You compute it at n equal to 2. This is the one that we wrote first as a result of one-dimensional Higgs theorem or whatever. This is just a calculus integral. So this, but it's related to this sum over graphs, which is like that. So that's yeah. So if we go 100 minutes, we are okay, right? 250 minutes basically is the two classes, right? And we have been, so when did we start, by the way?
130.
1:30. Yes. 5 minutes left, right? Huh? How much left?
Oh, no.
1:30 and then to 2:30, and then we have 20 minutes. Oh, we need 20 more minutes.
Yeah.
20 more minutes. Okay, so that's great. We have time. That's great. Okay, so are there any questions? Okay. So we want now to prove that a result, again, another application to graph theory, which is beautiful. Yeah, actually, this is related to the question that you asked in the Zoom. Yeah, right. So yeah, this is the so in the Zoom you asked a question. So I don't have, well, there is no answer, but there is something which is quite relevant, and it has a very important. Any question about this, by the way? Okay. So let me just what we want to do now is to show that there is a claim. Again, this is not a famous result, but we have to understand what it means really. So sigma one over order of automorphisms of gamma. Gamma belongs to G and K. Right? Is equal to yeah, n to the power 2k over 2 to the power k. K factorial, n factorial. Okay. Well, of course, what is G and K again of my notation? Is the set of all k-valent graphs with n vertices. Set of k-valent graphs with n vertices. Let me make sure that I have this correctly. Oh, no. No. That's not what it is. G and K, yeah, one notation G and K is the set of, okay, so to be very precise, isomorphism classes of, to be precise, of graphs with n vertices and k edges. That's exactly the question that I was asked actually from the Zoom. Of graphs with with k edges and n vertices. Set of adjoint classical graphs with k edges. Do I have it here? With k edges and k edges and n vertices. I mean, this is a finite set, right? Obviously, and that's so. The question that came from Zoom was that what is the number of graphs with k vertices and n edges all together, right? That was the question. Now that problem means computing this, right? Sum 1 gamma belonging to G and K. That's the sum. That would be the number that we want to compute. I said we cannot compute this number, and most probably that's correct. There's no formula for that. But when you divide by order of automorphism groups, there is a formula. And this usually happens in mathematics and also physics. When you divide something by order of automorphism groups, it's a much more intelligent summing as opposed to forgetting about symmetry of the object and just sum over all isomorphism classes. So here we are taking symmetry, internal symmetry of each object into account. Okay? And there are a lot of formulas in mathematics, for example, in number theory in many places. And also, I'm pretty sure in combinatorics and physics, where this 1 over automorphism gamma. So weighted number of. So this is basically kind of average or weighted number of graphs with, I mean, this thing. So this is not the number itself, but it's kind of weighted or average in some sense. And this happens a lot in mathematics. So we are going to prove this actually maybe today. And you see that the answer, the question that I was asking, has an answer in this form, but doesn't have an answer in this form. This is a very important point. So let me give you an example, which is kind of very interesting. But before doing that, the example is imagine someone asks you how many finite sets are out there. Okay. So let me tell you. Let me ask. So here's an EG. How many finite sets? Now you would say, well, obviously infinite, right? Well, there's only, I mean, there's one, two, there's one set, I mean, order one, there's a one set of order two, one set of order, and it goes on and infinite. However, if you take into account the symmetry of these sets with n objects, there's going to be n factorial. So the intelligent answer to that question would be sum 1 over n factorial. So this is equal to sum 1 over order of automorphism plot. I mean, this set 1 to n, which is sum 1 over n factorial, and that's E. So you can tell that the number of finite sets is actually E, 2.71 or something. You see, this is called categorical or categorical summation. And it's a very important idea actually in combinatorics, in number theory, in math, in physics, everywhere. That's a very important idea. We are not very good at counting. This is very coarse to try to count the number of things per se. Count them up to symmetry factors. And those symmetry factors exactly appears in Feynman's formula. So your question has some answer, and the answer that is here. I'm going to prove it now. So this is in Etinghoff paper. Paper. I'll just follow this proof. There are combinatorial proofs of this for sure, but let's give the proof of theorem. So to prove this, let's try then to compute the following again one-dimensional integral 1 over root g. I mean 1 over root 2 pi integral minus infinity plus infinity exponential of minus 1/2 x squared plus g exponential of zx dx. Okay, so this is a kind of complicated potential we are putting on the interaction term, which is g exponential of zx. I mean, dx should be down here, by the way. Of course. So here, this is a problem that gi is equal to g for all I, obviously. And bi is equal to z to the power I, the number z to the power I. H bar is equal to 1. And yeah, I mean, you can expand this in terms of powers of this term, and then you get that all GIs are equal and BI are Z to the power I. So, okay, so then Feynman's theorem tells us that this integral, so let's call this star, star is equal to this sum over graphs, actually, like this sum, Gn, and bigger than or equal to 0, sum in front of each Gn is Z to the power 2k over absolute value, I mean, number of the symmetry factor of gamma. Gamma belonging to G and K. Right. So you get this expression. But this expression is not quite the same as what we had in Feynman's theorem. But if you go through it, in this case, you see that it boils down to this. It's the same thing as this. Okay. So now we are going to compute this in a different form. Right. So this is what Feynman's theorem tells us. Now we are going to compute it actually directly, that integral. Like previous example. So let me compute star directly. We can just say that, okay, star is equal to 1 over root 2 pi, 1 over, okay, so let me write it, 1 over root 2 pi, and then we have got sigma, and from 0 to infinity, Gn over n factorial, integral exponential of minus 1/2 x squared plus nzx dx. obviously what we are doing, we are expanding exponential of what term was that? Exponential of zx in terms of powers, and then you get this term. I mean, you just write it as e to the n zx, and then get it. You get this term. Okay, then we complete the square, so to speak. This is equal to sigma now, and from 0 to infinity, gn over n factorial integral exponential of minus 1/2 negative x minus nz squared plus n squared z squared via dx, and then this becomes equal to sigma n from 0 to infinity gn over n factorial. Oh, there should be a 1 over root 5 gn over n factorial. Okay. 1 over root 2 pi. We just basically separate these terms. I mean, okay, I'm writing it again, but that's okay. Integral exponential of minus 1/2 x minus nz squared times exponential of z2 n2 over 2 dx. I mean, the point is that there's no x in this factor, right? It just separates, gets out of the integration. This is just the Gaussian shifted, the center shift. That's this term is just Gaussian is one-dimensional Gaussian. Okay, so then this becomes equal to some gn exponential of z2 and 2 over 2 divided by a factor. So then we have to put Feynman's result in this calculation match them. So the conclusion is that sum then over k, sum gamma belonging to gmk z to the power 2k over order of automorphism of gamma is, we know that now is equal to exponential of z squared n squared over 2. Yeah, equals to z squared n squared over 2 divided by n factorial. Right? So these are power series. So expand this as a power series, right hand side, and then we compare power series instead. Okay. So if we do that, compare Z power series. Then what do we get? We get that indeed yeah, I mean, the coefficients of Z on both sides have to be the same, obviously. So the power series in Z, and they should be the same. So this tells me that here it gives me that actually sum 1 over all of gamma gamma belonging to G and K is equal to and K, which is what we obtain here. 10 to the 2k divided by 2 to the k. K exactly. And possibly. Right. I mean, this number obviously need not be an integer because this is sums of this thing. I mean, it would exactly like this case doesn't have to be an integer. But this is the intelligent number. I call it intelligent just for now. Intelligent way of counting number of all graphs with k vertices and n edges or something like that. So, no, of course, the challenge here is to come up with that potential. That was the challenging part, not obvious part. I don't know who did this calculation first. Maybe Sixon Zuber from late 1970s, but it could be earlier. I don't know.
What's the inspiration behind coming up with that?
Yeah, that's a good question. Well, I don't know really. There must be some logic behind these choices. Yeah, I think so. But I'm not. As of now, I don't know really. Yeah. All right. So, any questions? I think now we are good. We can stop. Exactly. Any questions in the Zoom? Okay. Looks like there are no questions. Okay. Well, thank you very much. So I'll just stop.